Yes, so hello friends, this is the video tutorial for today's GFG problem of the day, which is and in range. So let's read to the question. You're given two integers L and R. Let me make this bigger. Find the result after applying the series of bitwise AND operation on every natural number between the range L to R, including both. So what the question says is, let's say the first test case, it is that L is 8 and R is 13. So we'll need to find the AND of all the integers that are in between L to R, both included. So that is 8 and 9 and 10 and 11 and 12 and 13. So yeah, looks pretty simple. How you can do this is just like do an AND operation for all the integers from L to L plus 1 to R, right? This is how you will do it. But the thing is that if you look at the constraints, so the constraints are that L to R is around 10 is to power 9. So if it is 10 is to power 9, so the maximum width of the integers between L to R could be as big as 10 raised to power 9. So you will have to go over all of them, and that would take 10 is to power 9 time, and that would obviously TLE. The maximum amount of computations you can do is around 10 is to power 8, or in a very okay, so yeah, it's around 10 is to power 8. So this would TLE. How you can optimize this is, see, you do not okay, so we are dealing with bitwise AND operations, right? The what are the properties of bitwise AND is that, let's say, 1 and 1 and 1 and 1, this is 1, right? But even if after having 4 ands I add 1 0, I even add 1 0, this would become 0. And now after becoming 0, this can I cannot do anything with using bitwise AND, because see, after it becomes 0, I cannot add another one and say, okay, now they cancel each other out. No, this would remain 0, right? If this would remain 0, so should I not focus rather than on ones? Should I focus on the 0? Like, is there a 0? If there is a 0, the bitwise AND would be 0. Now, this is at 1 bit levels, but I want to deal at integer levels, right? I want to deal at integers, so we'll break our integers down. So 8 and 13. So 8 would be what? 1 triple 0. 13 would be what? 1 1 1 0 1, right? This is 1 2 4 8. Yeah, 8 plus 4 plus 2 plus 1. So we'll break our integers down into bit representation. Now, see, as I saw that the L and R can be as big as 10 raised to the 9. So if this is around 2 raised to the 30, and if this is around 2 raised to the 30, we'll only have to deal with 30 bits. So 30 bits. So now we can deal at each bit level. Now we can see that for this bit, is this bit in between L to R in becoming 0 at any place? So like we can see, okay, so this is 8. This would be 1 triple 0. My bad. So this would be 1 triple 0. Now let's take all the integers between 8 to 9. So that is 1 triple 0. Then next would be 1 0 0 1. This is 9. 1 0 1 0. This is 10. 1 uh, 0 1 1. This is 11. 1 1 0 0. This is 12. And 1 1 0 1. This is 13. Now we have to do a bitwise AND of all these values. Now, see, for this bit, we'll see, is this bit becoming 0? Oh, no, this bit is never becoming 0. So in our final answer also, this bit would be set. Now for this bit is 0 at the first place only. So it would never become 1. So this would be 0. Similarly, this would be also 0, because this, see, at this place there are multiple zeros. So 1 0 triple 0. This is the final answer. Okay. So we have some things that we can better look out for. First is that we'll deal at integer level. The second thing that we got to is that rather than finding the count of ones, count of zero, we also only need to see at each integer, is this bit ever becoming zero in between L to R. Okay. But the thing is that how you will do this, if you again do a brute force implementation, go over all the L2R and do an early exit. Early exit meaning that if you ever see that at this bit, this for this integer x between L to R, that bit is not set, so you will do an exit. But that would also do how many computations? See, if R is very large, 10 is to power something 9, around this value, then for the first bit there would be 2 raised to power 30 times this is set, and then it would become unset, right? Unset. So you will have to go over all these values, and then you will see that okay, this is unset. Or if R is not so large, R is in that set, R is that all of them are set only. So we will again have to do 2 raised to the 30 computation. Again this would TLE. So you cannot like brute force this with an early exit. How you can then implement this is C. There's a cool property about bits, or the how integers are represented in bits. So let's take this example. This is all the integers between 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, sorry, this is starting from 0. My bad. Okay, can I move this down? Okay, let me rewrite it only. Okay. Alright. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. See, what the cool property is, if you do not know this, if you know this, well and good, is that see, the bits at uh, so this is the first 0th bit, this is the 1th bit, this is the second bit, this is the third bit. Now the bit and 2 raised to the bit at b, let's say this is bit b, this will form a group of 2 raised to the power b plus 1. Basically here there's a group of 2 raised to power 1 size, 0 plus 1, that is 2 size. So we can see 0 1 0 1 0 1 0 1, and this is a repeating pattern. Even here it would be 0 1. Okay, now here this would be this would be forming a group of 2 raised to power b plus 2 raised to power 2, 1 plus 1, right? So here we can see this is a group of size 4, this is a group of size 4. Again here it will form a group of size 8, right? So if these groups make sense to you, can we use an exam? Can we use this grouping property? See, if it is a group of 2 raised to the power b plus 1, this group would look like first 2 raised to the power b numbers would be 0, and the next 2 raised to the power b numbers would be 1. 0, these are all zeros, and then these are all ones. These are all ones, 2 raised to the power b ones. Right, we can see here 2 raised to the power 0 1, then 2 raised to the power 1 1, 2 raised to the power 0, 2 raised to the power 0 ones, 2 raised to the power 0 zeros, 2 raised to the power 0 ones. Okay, so now see, for each bit, can we now say that for each bit b, if L is in first 2 raised to the power L, 2 raised to the power b, then this bit would not get set else. I'm basically saying that L is, let's say, starting from here. So at L only this bit is not set. Else, see, else L is at here. So else L is in this second 2 raised to the power b. Else, so at L is this set. We'll uh, find next position at which uh, bit is unset, and at this position check if this is less than equal to r. So check that this position is in this r set. If it is less than equal to r, again this would not get set. If this is not, if not, set b bit. Hopefully this makes sense. Now how we can do each of these checks is that first check is we'll need to check that if L is in the first 2 raised to the power b values. So how you can do this? See, we are forming a group of 2 raised to the power b plus 1 size, right? So how you can check is that the first bit, that the position L is in the first C. Let's take the example of 0 0 1 1. So at 4, basically at the first bit position, the group of size 4. Now when we do a modulo of 4, these values would be like 0 1 2 3, right? So we can see here that this is 0 mod 4 would be 0 1 2 3, and then this would again get repeated because see, this is a grouping. So for grouping, the modulo of this would be same as modulo of minus 4, right? So for this, we'll just check that L modulo 2 raised to power b plus 1 is less than equal to 2 raised to power b, or rather just less than. If this is, then this is that L is that to this bit is not set. So basically, we are saying that here L is in this part. If L is in this part, then that this condition is not satisfied. Then we'll go here. So we'll go here. We'll find the next position. So next position. See, these are all ones. After this one, a zero will occur. So what would be the zero position for this is basically, if let's say this is some group G starting from top, this is some group G. So this would be the starting position of group G plus 1. And what would be the group of this is basically, see, the each are of size 2b plus 1. Each group is of size 2b plus 1. We are at L, so L would be in L divided by 2 raised to the b plus 1 group. So G will, this is our group that is that in which L is. Now we'll find the next group, which is just G plus 1, and the position would be G plus 1 into group size, which is 2 raised to 1 B plus 1. Hopefully this makes sense. I will show you the code. The code is a bit simpler. Also, what would be the time complexity? Now we are just doing an O of 1 operation on each bit, and number of bits could be 30. Right, let's go to the code. So I've created this answer variable here. As I said, we'll go over all the bits. No, I've created in long because we are dealing with 2 ratio 31, which can overflow. So I've stored this in longs. So this is basically group size. We can say group size is a better name here. And yeah, so this is group size. Where were we? L mod group size. Okay, I have misspelled group here. My bad. Group size. Are we using range anywhere else? Where are we using range here also? Yes. So group size, and this is count. Count is basically 1 raised to 2 raised to a b. So this is, so first check we are doing, that is this position greater than equals to count. So position here is L mod group size. If position of L is greater than count, so that is that at L this is set. If this is set, now we'll check that what is the next position at which. So we saw this G is what, L divided by group size, so G plus 1 into group size. Now if next is greater than R, then that next position at which the zero is also greater than R. So all at all positions, this is this this is 1. So we are adding that count, so that bit to the answer, and finally returning the answer. So basically what I mean here is, see, in this example 8 and 13, 8 and 13, we can run this also. So for 8, what would be our position? That is 8 mod for this basically. So that would be 8, and this 2 ratio of b plus 1 is 2 raised to power 4, that is 16. So 8 mod 16, that is 8, and now 8 is greater than 2 raised to power b, so that is 8. Rather 8 is greater than equal to this one, right? Yeah, you see, we are doing greater than equal to check here. So 8 is greater than equals to 8. Now we'll find the next. So next is what, this group is 8 divided by 16. So the current group that you are on is 0th group. Next group is 0 plus 1 into group size again is 16. So that is 16. So at 16 number, this bit would get unset, but 16 is greater than R. So that is why we are keeping this one bit. Hopefully this makes sense. I think I've over explained it, but it's fine. Thank you for watching. If you like this video, if you were able to understand it, like it and subscribe. Bye bye. Thanks for watching.